Usually, physics focuses on how a single charge generates its own electric field. But we are looking at a different scenario. What happens when an object enters an electric field that is already established by something else? Imagine a vast, invisible grid that flickers to life. This is a uniform external electric potential, generated by massive charge sources positioned so far away they are effectively at infinity. Any object placed into this field follows a specific physical law. It will move towards its lowest possible energy state. In these systems, reaching that minimum energy is the definition of stability. We can observe this behavior by testing 3 different objects within the grid: a single lone charge, a pair of charges, and a rigid structure called a dipole. Calculating the potential energy for these objects is a way of measuring the physical work required for an outside force to move them into the field and hold them there, against their natural tendency to fall into a stable position. We'll start by bringing a single positive charge from infinity and placing it at a specific point inside our external field. Here is our charge at point R. Its potential energy, U, is the charge, Q, times the external potential, V. For electrons, we use the electron volt. 1 eV is the energy gained accelerating across a 1-volt gap, equaling 1.6 times 10 to the negative 19 joules. The math becomes more complex bringing a second charge from infinity into that same external field. This second charge has to fight 2 forces at once. It requires work to move it against the main external grid, but it also has to overcome the repulsive field created by the first charge we placed. In this diagram, you can see both interactions. To find the total potential energy, we add the individual energy each charge gets from the external field to the mutual interaction energy between the 2 charges. As the number of charges in a system increases, the total energy calculation must account for both the influence of the external environment and the electrostatic forces between the charges themselves. Consider an electric dipole, a positive and negative charge separated by a distance 2a. The external field pulls them oppositely, creating a twisting torque. Using an external force to rotate this dipole to a new angle performs rotational work, injecting energy like winding a spring. We define the 0 point for this potential energy as the orientation where the dipole is exactly perpendicular to the field lines. At this 90-degree angle, the work done against the field is effectively 0. This rotational work, stored within the angled position of the dipole, is what defines its potential energy in an external field. We currently have a dipole held at an angle, suspended in a state of high tension by an external force. When that holding force is removed, the field's torque takes over. The dipole swings through the grid, locking perfectly parallel with the field lines. This diagram shows the dipole in its aligned state. Mathematically, since the angle theta is 0 and the cosine of 0 is 1, the potential energy equation simplifies to U equals negative P times E. That negative sign indicates that the system has reached its absolute minimum energy level. It has found the most stable configuration possible within the field. If the dipole were forced to face the opposite direction, 180 degrees away from the field, it would be in its state of maximum potential energy and highest instability. This natural move toward lower potential energy is why external fields reliably influence orientation of dipoles, guiding them toward their most stable configuration within the grid.